Welcome to this second video about elliptic curve cryptography articles that we break down and look at, analyze, annotate, try to give intuition for. Um, I babbled quite a bit in the previous article. I think it was more of the foundational one, giving the, basic intuition for what an elliptic curve is. So this time we actually look at Vitalik's post on exploring elliptic curve pairings. So as I said last time, so this time what we're doing is we're taking an elliptic curve, adding an extra structure called a pairing, and trying to give intuition for what that thing is, what it's used for. Um, so the main application for this that I want to look at are KZG commitments. And that will follow up in the next video where we analyze Dankrad's post. Um, so this post is kind of an in-between. This article by Vitalik has kind of two goals. One of them is just to, you know, give an intuition for this pairing object that we can then use as a black box structure. And that's kind of the place where I want to go today. I'm trying to go as quickly as possible to Dan Grad's article to focus on KZG commitments. But the second part of this article actually discusses um, with code how to construct the simplest pairing, which is the tape pairing. There are basically two main, as far as I understand, there are two main kind of pairings that were constructed originally by mathematicians, the tape pairing and I believe it's the wild pairing. And nowadays, as far as I understand, all of the implementations use some kind of optimized version of the tape pairing. I think they're called kind of actually optimal eight pairing or something, not tape pairing, but eight pairing. I will dive into all of those in a later video because I'm actually quite curious and I don't understand the math or the implementation there. That being said, today I'm trying to focus more on the pairing object, like the mathematical structure and how it's used, and to get us towards a place where we can use it as a black box for KZG commitments, BLS signatures, all of that fun stuff. Um, so okay, let's dive right in. So as I said, it starts with a trigger warning math. This is an article that Vitalik wrote in 2017. So here I am, 8 years later, probably 20 years older than him when he wrote it. And I'm going to be skipping out on a lot of the math, but that the tape pairing part. Um, but still, let's dive in. So okay, last time when we were talking about the the Cloudflare article, we looked at this elliptic curve that we have right here, um, and we talked about the point at infinity, for example, which you can see as kind of I mean that's how I like to draw it, um, because then there is an embedding, from the points FR into the elliptic curve, where a point x is mapped to g to the x or xg, depending if you use the additive or multiplicative notation for the group. Um, and so you have this clock arithmetic kind of mapping onto the elliptic curve. That's the intuition to have. That being said, so what we have here is we say a group preserving operation, right? This embedding kind of pushes the additive operation, boom, onto the elliptic curve. And let me draw right here. So what we're doing is that we have, let's say FP, and then we have let's say the elliptic curve EC, and we have the kind of, I actually don't know what this is called. I call it the embedding, but it's probably an actual better term for this. But so we take A and we map it to a G, where G is some chosen generator of the elliptic curve, can be anything. So again, this is either, so let's say here we're doing elliptic curve with the operation being plus, so that AG is equal to G plus blah blah plus G a times. Um, so you should get comfortable with switching between these notations. Sometimes you'll see G to the A, sometimes you see AG. It does get quite confusing, but after a while, you'll just kind of need to learn that, oh yeah, I mean, different people do it differently. And so you just need to, kind of get used to your brain, like when you're reading, oh, which group operation is he using? And then the notation will change. So for example, a multiplication will become an exponent if you're, in the multiplicative structure instead of the additive structure, all of that. So it's just a quick switch. It does get annoying that there's no one standard way to represent these, but it is what it is. Um, okay, so a lot more babbling. What was I talking about? Okay, what I wanted to say, right, is that this thing here is a map that preserves the additive structure. So remember that the field here has a plus and a times, right? So we take field elements, we can add them, we can multiply them. Just think of the natural integers here. Um, so if we take B, we can also map B to AG. And if we take A plus B, this maps to A plus BG, which is also, interestingly enough, equals to AG plus BG, right? Um, okay, so I I I think of these things. I know absolutely zero category theory, but I do think knowing the very basic, which is just like learning to draw a commutative diagram, really helps for kind of getting a visual understanding for these group structures. And the whole point of category theory is just representing kind of structure preserving maps. So we're not going to anything fancy here. All that I want to do is to show what we say when we say that a mapping is structure preserving. We mean that, so if we draw this diagram, so here with the mapping being just like A goes to AG. So this mapping here, and we have a mapping here, which is the plus, which stays in FP. So I mean, we draw it like this, but we mean that this plus takes two elements from FP and maps them together to another element. And then here we have the same embedding, right? Because we're still in FP, we still have the same mapping down here. And interestingly enough, we also have an addition here on the elliptic curve. And so what we mean when we say that this mapping preserves the plus structure, the additive structure on the field, it means that this diagram is commutative. If I start here with any two elements, AB, A and B, I can push them as A, G, and sorry, BG, or I can push them down as A plus B. And either route, so here I will get A G plus BG, or if I go this way here, now I get A plus B times G, and these are equal, right? So this is what this means, and this is quite nice. Basically, you really need to think of a function takes a set of elements, pushes it to some other place. Now, when we say that it's structure preserving, it means that this mapping not only pushes the set, it also pushes the structure with it, the structure here being the addition. So you think of all these numbers, right? The field elements that are related by this addition plus, right? Just think of plus as like the relation, like, oh, these two give this. This is like one struct. These are kind of related by this, all kind of pairs of this relation plus are related like this. When you push it to the other side, you push it to the elliptic curve. You keep this relationship between all of these elements. So they're pushed to completely different elements now in 2D space, but they're still related by the exact same addition operation or multiplication if you've chosen that. Okay, so that's kind of the fundamental thing here. So we're keeping the structure, which is important for certain things that we'll see, but the thing that happens with this struct is that we actually lose we do not keep the multiplicative structure. So in other words, here I can also take AB, I can take A times B and I can push it here and push it to A times BG, right? This is definitely something that I can do. Um, but if I have here AB and BG, there's just no way for me to recover A times B G. Like this does not preserve the the multiplicative structure of the field. Namely because there's just no timed operation. It just does not exist on the elliptic curve. Okay, now that we have this out of the way, so this article starts with a very important thing, which is that elliptic curve pairing right here, bilinear max, are a recent addition to 30-year long history of using elliptic curves for cryptographic applications, including encryption and digital signatures. All right, there we go. The key sentence: pairings introduce a form of encrypted multiplication. So I should only highlight this, right? Encrypted multiplication. Um, so what are pairings? They're basically about adding another structure to this elliptic curve. They are about adding, we'll have an elliptic curve with plus, and then we'll also add a pairing. I'll just write P, which we can think of it as adding a multiplication. That it's much more complex than that. We'll see that it actually requires two groups, and we need to go to a third group to get the result. But it's basically now we'll have a commutative diagram which goes even further, and you can recover the multiplicative structure in some other group, which means you can't go back. The problem is you always want these one-way door functions. Um, so we'll see that we're able to push things further to recover the decisional kind of Diffie-Hellman problem or some kind of structure. We'll be able to recover some structure and tell whether, you know, whether A times B whether if I give you an element here, we'll be able to tell whether it comes from you know, whether its pre-image is kind of a multiplication of two numbers that we care about. Um, okay, that's where we're going. Now let's dive in. Um, So again, if we come back, okay, so here at the beginning, he's actually, so here's the link to the Cloudflare article that we did in the previous video. So again, he's just summarizing that what we can do on the elliptic curve is adding and subtracting the numbers like this. And we can also multiply a point by an integer, right, just Pn. Uh, So you see here he's using the additive structure on the group, which is nice. Um, Anyways, this is quite standard. Now we're used to this, so we can keep going. Um, okay, he also talks about the point at infinity. I think these are all things that the equivalent of 0 point arithmetic. This is the thing which I struggled to explain last time, but I hope you had time to read about it or get some intuition for it. Um, It's really needed to get the group structure. If it's not for the special point, you don't have the group structure with all the nice properties. Okay, so he keeps going on and blah blah blah. We have a generator point G, as we said, which is important for the mapping. And this we say it represents the number one because um, our mapping maps elements A to AG, therefore it maps the number one to 1 times G. So with this addition preserving mapping, it's sending 1 to G. So G is the 1 on the elliptic curve. Okay. Now, boom, that's enough for the introduction for Vitalik. He jumps straight into pairings. So here we are, pairings. What we will be able to do, as he's saying, is they will allow us to check whether or not P times Q equals to R. So that's what I was getting into. So what that means is that they make the decisional Diffie-Hellman problem easy, while keeping the computational Diffie-Hellman problem and the discrete logarithm problem that we talked about last time they remain difficult. All right, so these are actually about computing, like getting back to a number, and not only about being able to defer two elements. Um, so um, So basically, they'll give us an extra set of properties which we'll be able to use to do things like multi-signatures, like KZG commitments, all of these beautiful things that require adding points and at least being able to tell whether things were added. In part, we'll be able to commit to polynomials because polynomials are multiplying, you know, coefficients times elements. So already there you have a multiplication. So if you want to compare two polynomials, you basically a polynomial is addition and multiplications, right? So we need these two things. So again, all things that we'll dive into uh, in the next lecture. Okay, so third way to look what pairings do, what pairing is mostly limiting. Okay, so here he's also giving some more intuition. Um, Right. Again, like traditional elliptic curve math lets you check linear constraints. Pairings lets you check quadratic constraints. What is quadratic constraint? It just means you have something to the square. What is the square? It's a multiplication. It's all just like saying the same thing. And then the key sentence is that what I was just saying, the quadratic is enough to let us work with deterministic threshold signatures, quadratic arithmetic programs. So this post was written as the first of a series of posts that wants to talk about snarks, I believe. So yeah, right. So because QAP are used there. I won't go into that, although this is another use for these pairings, which is quite nice. Um, okay, so here we go. So what is a pairing? Here is where we need to go into or he actually introduces it. So a pairing is this. Yeah, I actually apologize for having skipped it. I should have introduced pairing. So what is a pairing? Is just this function EPQ. Um, it's a bilinear function. I think he says it somewhere. That's the most keyword, bilinear. So you've probably learned of linear maps in linear algebra. So if you have a function L that takes a vector. Typically, linear maps are on vectors, so it means that if you have a linear map that takes, let's say, a times v1 plus b times v2, this is equal to al v1 plus bl v2. That's a linear map. Bilinear just means that it's linear in both arguments separately. All right, so that's basically what he's saying here. He's saying that the e p q plus r. Also, he doesn't mention the multiplication, but the bilinear mapping needs to also carry over with to also work with the scalar mapping, right? So q plus r. So let's say we would say q plus ar, whatever, um, is equal to e p q plus. So okay, so here you see here's an instance. So he uses times here, right? So he's decided that for the basic group, the groups that are here, he's using plus, but in the target group, where the pairing maps to, he's using multiplication. I think that's just to, kind of syntactically be able to see that the plus is in the pre-groups and the times is in the target group. But the point is already you're working with two separate groups potentially, right? So the first argument and the second are different argument, yet he's just using plus happily here. So I personally like to just use plus also because you're used to linear algebra where it's a map from a vector space to another vector space. You have a plus in the first one. You also have a plus in the other one. Um, so all that to say, you could use a plus here as well. It would also work. But I guess we'll just follow along with his notation. So E P Q. So I said plus, but I should say times E to P A R. And because the pairing also respects the scalar multiplication, you have P R to the A. Um, Okay. So that's the idea. We'll see that we can do a lot of things with this. Again, we'll go into the details of how we actually use this linear structure in KZG commitments in the next post. Um, the craziness is that we can even build such a map, which is kind of what Vitalik is trying to go get at in this article. But I will skip most of that. But I still want to continue and give some more intuition for what's happening. So, okay. Um, let's see. So now he starts wanting to, okay, I do want to give a bit more intuition, I guess, before we go on, because I feel like I didn't. Um, okay, so just to make it clear and write it down, so we have group, let's say G1, G2, and G3. And so E is a function from G1 cross G2 to G3, right? Where G1, let's say, what we're saying is that G1 is actually a group with plus uh, X here is not multiplication, it's just the cross product of these two groups. G2 with plus, and it goes to a group G3, which uses multiplication as its operation. Um, okay, so I mean, but that's effectively the idea. So, and then I personally like to just use plus because then you can do very simple things with the pairing, like when you define it as just E, like let's say AA plus BB C equals 2, and then it just opens up. Literally, you can think of when you're keeping C constant, then you're linear in the first argument, right? So this thing here is linear in the same way that the L here was. That's what bilinear means. So what you get here is just that you get A E of AC plus B, oops, E times E um, of BC. Okay, I think that's enough, but at least I wanted to write it down because I feel like Vitalik kind of skimmed over these details. Just having the right syntax sometimes is 90% of the you're 90% of the way there. Um, okay, so to get back to this, if P, Q, R, and S were simple numbers, okay, so what is he doing in here? Note that plus can be arbitrary. Oh, interesting. So here up here he does say that he does mention what I was saying, that the plus and times are just arbitrary operators. Okay, so if P, Q, R were simple numbers, making a simple pairing is easy. Okay, yeah. So here we'll see why quickly. Why people kind of use plus for the first group and then multiplication for the second group. And it comes to this mapping, most people think of it as an exponential. That's also why we call it the log, the hardness of the log problem. Um, so he's saying like just take e to be 2 to the xy, x times y. Um, honestly, it's a good exercise to also just try it with this definition, xy, right? You'll see that this also works. But 2 to the xy again is just like nice notation. So, okay, so if we take this an example, E3 comma 4 plus 5, and this is equal to 2 to the 3 times 4 plus 5. So 3 times 4 plus 5, and then so it's 2 times 2 to the 3 times 9, 2 to the 27. And oh, so he shows the linear structure here. So okay, blah blah blah. You can play with this. He basically shows so this gives you the intuition for what you should be thinking of geometrically at least. There's also an awesome video by 3 Blue 1 Brown that I recommend on just like this famous equation like e to the what is it minus I pi or something minus I forget what it is. No, it's 2 pi or something equals e to the minus I theta. Jesus. Um, Okay, I'm blanking, but basically where he explains the there's this one and the FFT one where he, basically uses this relationship where you can think of EI theta as going over the circle, the complex number circle. Um, and so you see that, like, this EI theta again is like the exponential map shows up everywhere. Okay, so got to quit babbling here and make some progress. Okay, so what's the idea? So the idea is we start with R plus going to R positive greater than 0, right? So, okay, we have this map e to the x, which is what we've defined our pairing to be. So we're taking, a number, whatever, a, and it's going to e to the a. So, this graph is just this graph that we're all used to, the exponential graph, e to the x. This is the function e to the x. Okay. So what's the issue with this? The issue with this is that we know that there is a function called log. Actually, let's call it ln, which is log in base e. We know how to compute the reverse of this function, right? So it is literally a bijection. This is really bad. We talked about in the previous article, the whole point of crypto is you want trapdoor functions. This is not a trapdoor function. So this doesn't work. Okay. So, well, first of all, we got to do a two-step. So we can repeat the same game. So I guess there's two mistakes with this. First of all, it's not a trapdoor function. Second of all, it's in R, so that's like, computers do not deal with the real numbers. They deal with discrete numbers. So let's first draw this. So we can take the mapping 2 to the x that goes to z greater than 0 x. So when I write this, I just mean that this is the z is the group of integers. So it's like minus infinity, minus n, minus 1, blah, 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 0, 1, 2, like this, up to infinity. So all the real numbers, with the plus here, meaning we only look at the additive structure, not the field. And okay, so when we take this exponent, so also we're going to the positive numbers, so now it's the positive integers, so we're going to, 1, 2. Actually, we're not even going to all of them, right? As you may have noticed, because 1 goes to 2, 2 goes to 4, blah, blah, goes to 8. So we only have some of them. But whatever, we can say it's a subset of the natural numbers. In any case, this also easily has an inverse. So, okay, now we can work on a computer with this, but there's an inverse, therefore it's not a useful cryptographic function. Okay, so what do we do next? We go to modular arithmetic, which clock arithmetic, which everyone is used to. What did I write here? Oh yeah, I see. So we can do the same with AX. We could still take 2 to the x. It doesn't matter. We take any number. Okay, so here, in most cases, in math and crypto, using modular arithmetic works because kind of the modulus creates enough of a, kind of weirdness with the group wrapping over itself that taking powers is not able to be inverted. That being said, there are some very advanced techniques called index calculus. And index calculus basically are a bunch of techniques that you can use to, I mean, the same way that we could not break, but effectively search through prime factorization, that we have algorithms for factoring two large prime numbers. Kind of the same thing applies here, and we have this thing called index calculus, which also allows us to effectively kind of reverse this operation. It's definitely much harder than in the integers, but it's still doable, and much faster than exponential search. So this wouldn't work for a cryptographic primitive. So okay, so this is basically why we need to go to elliptic curve cryptography. I think this is something I should have mentioned in the previous article, but this is kind of the reason why elliptic curve cryptography took over. So instead, we have this mapping, right, which is just AG, let's say. A goes to AG that we're used to. But the point is now instead of staying in the one-dimensional space, we go to this two-dimensional space with a weird addition that looks like a billiard ball moving around. Um, and this, after 30 years of searching, we still, this thing is still computationally hard. So, meaning as our computers are getting exponentially faster, we just need to increase the number of bits to get to keep the same amount of security. Um, so, so that's beautiful. And that works. And this is why the curve cryptography is everywhere nowadays. But what we want to look at now is instead um, to give us more properties. So elliptic curve plus a pairing. So when you add this weird structure, the pairing that we saw here, right? Um, again, the pairing here is defined on three groups. Um, I think these three groups are all related. It's going to be, we'll touch about it. It's like field extensions of the same group. You can think of all of, for first kind of intuitive introduction to this kind of material, just think of all the groups as being the same. Think of the pairing as taking two elements of the same group and mapping to the same group, right? I think that's the right way to think. So here, think of this pairing as just being kind of a literally like a multiplication, right? So the elliptic curve gives you plus and the pairing gives you times. So the plus here takes two elements of the elliptic curve and it maps back to itself, and the pairing would take two elements of the elliptic curve and map it back to itself. That is not how it works in practice, or in theory, but you can at least think of it this way until you actually understand, the construction, the tape pairing. We'll go into all of these in later articles. Okay, so the nice thing is here is we're adding a bunch of structure to the elliptic curve, but somehow this is still hard. Still hard. There is still no, even though we've given a lot more structure and a lot more information um, to people who get access now to these group elements, they actually, these elliptic curve elements, you still cannot use this pairing to go back, which is awesome. It makes though the decisional Diffie-Hellman is now easy. Okay, so what is this? Let's talk about this real quick. Okay, so I just want to talk. So we'll say the three things that he mentioned above. So we have the decisional Diffie-Hellman, and then we have the computational Diffie-Hellman, and there's another one that I'm forgetting. Oh, sorry, there is the discrete logarithm problem, which are all related. So okay, so we'll see first the discrete log problem. So that is still if you have an element, right? So if fp, you go to g to the elliptic curve, and if you so you have a, let's say a p, well, no, okay, not a p. Let's say an a, you map it to ag, um, right? Or g to the a, of course, depending on how you represent the elliptic curve. Then going back is like, can I find back the a? It's called the log problem, again, because of, this, when you represent it with multiplication, g to the a, you want the log, you want to get back the a. So this is still not possible. Not possible. Okay, now we have so two, we'll look at the decisional and the computational. Diffie-Hellman. Diffie-Hellman. Okay, so remember that the decisional, sorry, the Diffie-Hellman problem, the Diffie-Hellman key exchange, right? Was basically how do we get two people talking over an insecure channel to agree on a secret without anyone else being able to figure out that secret. So they're related to this problem because so you have a P, let's say you map it to PG. You have a Q, you map it to QG. Should have used A and B, but whatever. and P times Q maps to PQ times G. Okay, so the computational Diffie-Hellman is um, if I don't have access to this, am I able to compute it? So can I compute this based on only those two values? Um, right. So remember that this is exactly the Diffie-Hellman key exchange, right? One party chooses P as the secret key, the other one chooses Q. So and then they send this over to each other, and then they just multiply. In this case, like multiply by each other's respective private key to come with this. And basically, so all of the eavesdropper have access to these two guys. If they could reconstruct this, they would have access to the secret. That's what we don't want to happen. And indeed, this is not possible. So that's nice. That again is only because the the kind of the multiplication structure is not kept. Um, so right, because so it's basically the pairing gives you a kind of, it gives you a way to multiply things, but as I said, it's not keeping inside the group. Otherwise, if you could just multiply them and you would get this G. It's actually, it's mapping to another group, which is why this problem remains hard. So you will see what exactly it gives you. Um, but just be known that this is so you can still do even if you have an elliptic curve with an extra pairing gives you all these other nice properties, you can still do Diffie-Hellman key exchange in that pairing in that group. So if you have another RG, so um, can you distinguish both of these? Can I distinguish these? This is the decisional Diffie-Hellman. So it's just if I give you the real one, and a random other element. Can you tell me which one is PG, which one is QG? Um, sorry, that's not what I mean. If I give you this and this, can you tell me which one is actually PQG? Um, I actually think you might have access to these two. I'm not sure. Um, to be 100% frank, I don't know why the decisional Diffie-Hellman is interesting. I'm assuming it's I was going to say it's subtle. It's probably not that subtle. It's just a lack of my knowledge. I should definitely know why this is interesting. But I just wanted to at least like show that the decisional Diffie-Hellman. Oh, okay. I'm being stupid. So the decisional Diffie-Hellman becomes easy in the pairing group. Um, so actually, we are able to distinguish these very easily by using the pairing. Right. So we'll be able to push these out to this other group, G3 or whatever. Um, and that will keep the multiplicative structure. So we will actually be able to tell which one is which. Um, and this is kind of how you can think of something like signing, signing a signature, digital signature. You don't want to recover, right? You don't want to go back and recreate, kind of de-encrypt. All that you want to do is to make sure, was this actually signed by the this person? So being able to do that is one thing. The other one is KZG commitments. So pardon me, I was being stupid. But yeah, so the decisional Diffie-Hellman having broken makes it really nice for a bunch of other applications that we'll build on top. Okay, perfect. So now let's keep going. Okay, so now we're going back. So we've done like a kind of a big detour into I guess kind of basic cryptography. I hope it was useful. But now we're back to Vitalik, where he's saying to work on simple integers. Okay, right. So we're back to when he was talking about the simple pairing, right, and how it's broken, which was what we were going which was this basically, right? So there is kind of an inverse mapping for the exponent map, which is bad. So this is, I think here he's just describing what I was saying, right, with the public key and the one-way function. So I think now we've built all of this intuition. So this part, at least of the article, should be a lot easier to read once you go through it by yourself. I think with the background knowledge from the Cloudflare article really helps for sure. Um, and so, okay, so now he starts going into the craziness of this group, right? This special group that I was talking about, the G3. Um, it's what's called an FP to the 12 element. So what is to the 12? Or basically, right, literally as you can take a cross product of groups like A cross B, now you're taking like A cross blah, 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 cross A 12 times. So you're building kind of this gigantic, you know, vector space, if you can think of it this way in a sense, but it has like much different structure. So that's what this is. He does not explain kind of where it comes from. There is an article, really nice article that came out much later than when this was written. Um, it's part of the ETH2 book now. It's called BLS 12 through 81 for the rest of us by Ben Eddington. So I really want to read that article. I think I'll do as a separate viewing at some point once I understand it better. But it actually goes through the actual construction of these with the torsion group and how you can quotient them to make it still computationally feasible and make it fast on the computer, despite being, like kind of 12 elements. So that'll be very interesting. But for now, I think let's just read what Vitalik is saying. Turns out that it's possible to make binary pairing. Come up with a function E where the inputs are elliptic curve points and where the output is called. Okay, so right, so he's just saying it is possible. So now he's getting into territory where we kind of say, what is the target group? So we cannot make a pairing that goes back to itself. We have to go to this like kind of embedding group in a huge space, which has like even kind of scarier properties. But so we will, what I was saying is we will see the gory details on how this works when we look at the BLS 12 381 for the rest of us article. So, okay, we'll look at this in a future video. Um, okay, and then here, so if we use blah, 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 you can use logarithm to go backwards and everything breaks. So this is what I was discussing. Okay, so now he's going back to really, really simple things and just explaining, modular kind of clock, so-called clock arithmetic. So I'm going to assume that everyone knows about this. If you don't, you should probably make a little detour on Wikipedia. Um, this is kind of basic stuff that I think everyone should know. Um, okay, and then um, okay, yeah, I guess the one weird thing is the division here, which maybe people don't know. I have to remind myself. So Fermat's little theorem is basically just says that A, if you raise it to the power of p minus one in a group in the group FP, um, this will always be equivalent to one mod p, right? Okay, so what this means is for all A's, and this means that then that so if you do A times A to the p minus 2, right? This is just A p minus 1 is equivalent to 1. And what this means is that, when you have two elements that you can multiply and give you back the identity, it means that this is A to the minus 1. So this is the inverse. So that's basically what he's saying here. He's saying, so when you do A divided by B, you're basically, it's equivalent to doing A times B inverse. And so we're saying that this is A times what's the inverse of B? We set it here. So it's B to the P minus 2. And then all this you need to mod by P. So he uses this to mean mod. That's all that this is. Um, and then, okay, so, right, so that's basically it. He's going fast. I'm also going to go fast because now he's also going into extension fields. So now he's basically going towards the tape pairing. So um, I'm also going to skip a lot of this because I don't think it's that relevant to, it's actually not relevant at all to using or, to using a pairing as a black box application if you just assume that you have a pairing library and you want to use it to build things and understand the intuition. Understanding how it's constructed, surprisingly, does not actually help with much things. It's actually one of those very nice places where the abstraction is not leaky. right? It might be in terms of performance, but in terms of understanding and building things on top, I think it's one of the really, really nice places where the abstraction is not leaky at all. Um, so which makes it quite nice. Anyway, so here he kind of explains extension fields, which is kind of also how you construct, you start with the real numbers and you construct the complex numbers by adding I. So you tack on the second dimension, and then, the same way with A plus, you have to define an addition and a multiplication. So, the way you define multiplication, you guys are probably used to, let's say for complex numbers, um, is also weird, right? So you have to prove the properties, blah, blah, blah. So you can play with this. And so, yeah, okay, so he does mention, I can go quickly for those who are not used to, but let's say, what is this, right? So it's just, you're doing coordinate wise, so 8i plus 4i squared, uh, which gives you, so all of this, we remember, is still mod 7, so mod 7. So you do coordinate wise mod, so this gives you I plus 4i squared, which I squared is -1. This doesn't change, so it's -4. And so we can do, let's say, plus, 4 times -1. So this equal to I -4, or I think it's nice actually to keep plus -4. Both of these are mod 7, and -4 mod 7 is I plus 3. Okay. I don't know why I'm spending so much time on this, but so if we keep going here. With real numbers, the fundamental theorem of algebra ensures that the quadratic extension that we call, so sorry, I'm reading here. So again, I'm going fast. I do think that Vitalik, when he wrote this, probably also didn't understand all of this, is my assumption. I mean, it goes very deeply. And stating results is always easier than actually kind of understanding, deriving them yourself. Um, but all that to say that I just want to get to the important snippet of here. Um, okay, so basically when you tack on the I, what he's saying is that you can no longer make any more extensions of the complex numbers. So you take the real numbers, you tack on an I, you get the second dimension, you get complex numbers. Um, in order to do a field extension, you need to find what is it, kind of basically the theory requires that you find a polynomial, an irreducible polynomial. Um, there are no such things because all polynomials on top of the complex numbers are factorable. Right, that's the fundamental theorem of algebra. So that just means you're done. You cannot keep on building, attacking a third, fourth, fifth dimension. That is not true ever. It says with prime fields, however, we do not have this issue, so we can go further and make cubic extensions. Um, so with the prime fields, with the the computer numbers, we can keep going. We can keep going and add more dimensions. And this is kind of how you get to the 12th dimension when we had FP to the 12th. Um, so that's kind of where he's getting at. Um, and then, okay, this is the key sentence, I guess. And it is these kinds of supercharged modular complex numbers that elliptic curve pairings are built on. Right. So this is as much intuition as I wanted to get out of this. I'm not even going to claim that I mean, I don't understand the tape pairing, so I won't be able to describe it. I do want in a separate video eventually to actually understand it myself, present it, and go over this code. I think it would be quite interesting, but that'll be for another day. Okay, so now we actually see the structure. So we see that the pairing, right, that which was I was saying before, actually has three separate groups. Um, so the first one is just your G1 is just the usual group that we're used to. So as he writes here, the Weierstrass formula. I actually don't know why he doesn't have why it's not in the form y squared equals to x cubed plus ax plus b. Um, I don't know if pairings can only be tacked onto elliptic curves of this form, meaning a equals to 0. I don't think that's true, but I will need to double check that. I actually don't know. Um, And then G2, so when we continue, G2 is an elliptic curve where points satisfy the same equation as G1, except the coordinate are elements of FP12. So, right, so G1 is, let's say FP2, right? There's two elements of FP. It's a two-dimension curve. G2 is an FP to the 12. Um, and GT is the type of object the result of the curve goes into. The curves that we look at, GT is FP12. Oh, interesting. I actually did not know this. So, okay, so I guess they are the same dimension. So there is this thing with the torsion group where you can actually kind of, I believe it's called torsion, but one of them, or it might be both, you can kind of actually, there's a reparametrization that brings it down, I believe. I mean, for certain curves, for example, the BN 254 and BLS 12381 brings it down to, I think you divide by six, so it brings it down to level two. Um, or might be double the dimension of G1 or something like that, right? Because that's what you were used to actually. So G2 typically is uh okay, right. So let's say in EigenDA, we have our points, G1, G2 points for BLS signatures or whatever, even on Ethereum. Your G2 points are typically double the size of the G1 points. Um, and not six times, right? And that's because of this trick, which we'll see in the we'll see in the future video when we analyze the BLS 1231 for the rest of us paper. Um, and okay, so here he's again just talking and saying that the bilinearity is the most important property of the pairing. The other two that are very important is efficient computability. So it's very nice to have. I guess that's one place where the leaky abstraction is important, is that it's very nice to have this pairing. In theory, in math, we can construct all sorts of nice things on top, like KZ commitments. But if computing this in a computer, if computing the actual map E was extremely expensive, then it would be useless. So it so happens that that is not the case. It's not cheap, but we can definitely compute these pretty fast now. Um, and then the other one is non-degeneracy. So that's just like a typical kind of condition that you tack on of any interesting function. It just means that your kernel is not zero. Like you're not mapping all of an entire space with structure down to zero because that also preserves the structure, right? Mapping any kind of nice field or group or whatever to the zero element preserves the structure because you can define a plus and a times on zero, right? It just does nothing. So it does preserve the structure, but it's just like very uninteresting property. Um, okay, so we don't want that. Okay, so now the rest we're basically done at this point. So he's just this is the rest of the article, right, where he's giving intuition for the so this is the definition of the tape pairing. Tape pairing is defined here, like this. So I divisors are still difficult for me, so I won't even attempt to describe them here. Um, But so yeah, so you have to define these divisors, which he gives an example here, fxy is just a function looking at the zeros. It's kind of typical stuff. I think looking at the zeros and infinities, you do this in complex numbers as well. So I'm not quite surprised if this shows up, but I will be actually very curious to understand this structure better once I get there. That being said, so we'll just continue to the parts that are interesting for us, kind of the nice. Oh, right. So okay, so here, so for those who want to go down the rabbit hole, he says to prove some more results, you have to deal with notions like linear equivalence, Will of reciprocity, and the rabbit hole goes on from there. So he shares these, um, which we'll look at some point. Oh, and here is the optimal eight pairing. Okay, so this is the thing that I was saying. Um, there's a modified version of this tape pairing, which is called the optimal eight pairing, which I'm assuming is optimal because I believe that's what I've seen implement everywhere on ArcWorks or Gnark. Um, okay. And okay, so what does he say then? Okay, so the last part, which is of interest theoretically, at least to understand these things and kind of foot guns, is that every elliptic curve has a value called the embedding degree. Um, right, so what is this embedding degree? Um, right, all that to say, so if we go, note that the fact. Okay, yeah. Okay, so let's go back a step back. So let's start from here. This is kind of the, this should be called the conclusion. So we're back to nice territory, which is not too scary. But note that the fact that pairing like this is possible is somewhat of a mixed blessing. Um, so it means that all protocols that we can do pairings become possible. So lots of things. So we'll see KZ commitment in the next video. But it also means that we have to be more careful about what elliptic curves we use. Why is that? Because, so okay, every elliptic curve has a value called an embedding degree. Blah, blah, blah. This is defined like this. We'll see. In the fields above, k equals 12. The embedding degree is 12. Speaking of which, so in it, in BLS 12 381, 12 is actually the embedding degree, which is a fun fact. So it is also 12. And in the fields used for traditional ECC, where we don't care about bearings. Oh, right. So, okay. So I see. So in the fields above, and in the fields used in traditional ECC, so the ones, used by the Cloudflares of this world and the Googles of this world, where the pairing is not important, you just want to do Diffie-Hellman, more simple things. So the embedding degree is often extremely large. Um, so to the point that pairings are computationally infeasible to compute. Oh, interesting. Okay, so I think this, so this K is basically, if it's extremely large, you won't be able to compute the pairing. It'll be super expensive. If it's too small, um, if we are not careful, we can generate fields where, I don't know why he says field. I'm guessing he meant the actual elliptic curve and not the field because all of these are kind of live on the same field. Um, I'm not sure what he's talking about here, but oh, I think he means the field, like the field that is the order of the elliptic curve. Anyways, I will need to get back about this because I'm not quite sure. But basically, if you're not careful, and you can generate a field where k equals 4 or even 1. And in this case, and if k equals 1, then the discrete logarithm problem is broken. Um, right? It is, well, okay, it becomes much easier. This is the MOV attack. Um, and so typically you want to stay, this is why it says using curves with an embedding degree of 12 or higher ensures that this reduction is either unavailable or that solving the discrete log problem over pairing result is at least as hard as recovering a private key from a public key the normal way. Um, so here we have a Goldilocks situation where if you're too high of an embedding degree, you won't have a pairing. If you're too small, the pairing is going to be give too much information and make maybe breaking the cryptography easy. So you want to be in this middle spot, 12. I actually don't know if there are other numbers. I believe BN 254 is 12 as well. Again, some more studying that I need to do. Um, Okay, so with that being said, so I want to give one application before we move, like the simplest application, which is just ECDSA. So we have now this pairing object. If we look at ECDSA on the normal elliptic curve, so you just go on Wikipedia, type ECDSA, elliptic curve ECDSA, it's actually a separate Wikipedia page. You'll find this, right? And still quite a lot of crap you need to deal with. And mainly the thing is because, you're kind of poking your fingers into the actual like mathematical 2D representation of the elliptic curve. And a bunch of places we take the x coordinate, take the y coordinate, multiplied by some element of the field. So you kind of, you're not using the elliptic curve as a black box. You know that it's, in not embedding degree, but you know that it's in a two-dimensional space where both coordinates are also elements of the same field, and you can kind of, multiply these things. So we're kind of cheating in a sense. Whereas if you add a pairing, actually all of this becomes very beautiful and very simple. So let's do example ECDSA. ECDSA. So again, elliptic curve, digital signature algorithm with a pairing. Okay, so what do we need to do when we need to sign? We have a message and then we have a key pair and we want to sign that message, send it to someone. That someone has access to our public key and the message, and they want to just make sure that we the holder of the, the public key that signed this message. That's it. Okay, so let's define the spaces that we have. So M is kind of just the, abstract message space. And we have FP, which is the underlying field of the elliptic curve. And we have G1, okay, G2 and GT. So you kind of got to get used to using these other two groups, right? Um, so if you accept this crazy structure as a black box, everything becomes simple. You just got to get used to it. Okay, so what do we have? So we have a private and public key pair. So I just call them K. K goes to, okay, so typically you always have a choice. You can either put the public key in G2 and the signature in G1 or the other way around. So I'm just choosing to put K times G2 here. So this is this is the public key, and this is the private key. Okay, and now we also have let's say message here, message M, and then the message we have a hash function which goes to G1, so H of M. Note that this is a this is a separate function. It's a trapdoor function that doesn't preserve any structure, right? So it's not kind of, pushing M to FP and then doing, it's not doing M times G1, right? Like it's not doing this. It's just good old hashing to the curve G1. And to sign, what you do is you just basically do K HM, right? So you kind of do this. Um, okay. So these are the puzzle pieces, if we will. Right. So this is public. This is the message is public. The actually it doesn't have to be, but HM is public, and this is the signature. So this is just the public signature, right? Whereas, well, this thing is the private key is private. That one's separate from the others. So I'm going to color it differently. Okay, so now we have access to both the public key in G2 and the public signature in G1. Um, those are sent on they're out there on the internet, right? So someone has access to these two things. They also have access to the pairing. And I mean, of course, they know the elliptic curve, and they want to know basically whether these things match. Um, again, this should remind you, they kind of want to know, they have this and they have this, right? If they could reverse, right, do the log problem, they could just get back K and then they get the private key. This would be really bad. But they want to know whether this is related to this, but there's actually no way to know this either, right? Because the mapping, this mapping doesn't preserve the multiplicative structure, doing this. Okay, so what do we do? Remember that we have this function E, okay, so we have this function E, which takes an element of G1, an element of G2, right? So we have E of G1, G2 goes to GT. So we have this. So, okay, so what are we pairing? We're pairing, right, okay, so we have G2 here. So we'll take G2, this with G2, and this will give us E of KHM G2. So we have this pairing, we kind of pushed this item off to GT, and then we'll do the same thing here, but with this and this. So E HM KG2, right? And then the function, like the signature verification is just verify equality. So here we just need to verify that these are equal. And why does this work? Because if we take E, H, M, K, G2, but just by the pairing equation that we had, because it's bilinear, you can do G2 to the K, and then you can kind of just pop it back on the other side and get E, K, H, M, G2. Oops, G2. Right, so what's kind of crazy with this pairing is you have this K, you can pop it here, or pop it here. It's all equivalent because of the bilinearity. Um, but yeah, so what's happening is that we've actually managed to identify the private key without recovering it. So we've managed to, kind of identify the signer, the K, by multiplying, right? It's kind of multiplying K and HM. That's the signature. You're just taking those two things, scalar multiplying the element of G1. So here, but because this multiplication doesn't keep the multiplicative structure, but the pairing pushing it over does, right? It has a way you can kind of multiply, um, verify like a multiplication. Um, and then make sure that this public key actually sign this signature. Um, so, okay, that's the beauty of it. I should have done a better job explaining this, but I hope this at least gives some intuition for what's happening. This is our first application of using a pairing. It's the simplest. So I would suggest definitely take some time to redraw this yourself, play with it, see some equations, maybe look at this being written by other people. There might be different ways of writing it that might click better with your brain. But this is the main thing. So next time we're gonna play a lot more with the pairing by using it for KZG commitments. Um, so we'll look at Dankrad's article. It'll build off on this, but I think it's going to be a nice clean slate that is meaning even if you didn't fully understand this, I will kind of rebuild some of the pairing intuition in a different context. So I do think it's okay to go and watch the next video, even if you haven't understood everything that is here, because I will go through some of the material again in a different context, which might help get some better and different intuition. All right, well, thanks for watching again.